Hello and welcome to Engineers Mindset. So in today's class, we are going to be looking at atomic packing factor for FCC structure, otherwise called the face center cubic structure. So let's start by putting down our formula. Atomic packing factor, APF, is given simply as number of atoms multiplied by the volume of atoms divides by the volume of the cubic cell itself. Okay, now always remember to multiply this by 100% because APF is measured in percentage. Now I will start by plotting my simple cubic structure. Now, for a simple cubic structure, there are atoms at the edge of the corners. They are all atoms at the corners. So just shade all the corners to indicate atoms. Now, if you take a look at the formula, we said number of atoms multiplied by the volume of atoms, which means we need to find the number of the atoms. Now, these atoms at these edges are called corner atoms. Let's obtain total number of corner atoms. So, number of corner atoms this is going to be equal to, now be careful, if you count these corner atoms, you have 1, 2, 3, 4, 5, 6, 7, 8. It seems like you have 8 corner atoms, but that's not the case. When crystals are actually stacked or packed together, they are actually not giving their entire volume. Rather, they are actually pairing with other crystals to provide or give out their volume. So, which means this particular atom is providing, since we have total of 8 corner atoms, each of these corner atoms are providing 1 all over 8 of their volume. This is also providing 1 all over 8 of its volume. Same thing as this corner atom providing 1 all over 8 of its volume. So the entire corner atoms are providing 1/8 of their volume. And since we have up to 8 corner atoms, it means now that total number of corner atoms becomes 8 multiplied by 1 all over 8. And that will simply give us what? 1 corner atom. So the total 8 corner atoms combine to provide 1 full volume of an atom. Okay, but then we're talking about the face center cubic structure. How then, or what then tells us that this structure is a face center cubic structure? Simply because from the word face centered, which means there's an atom centered at each of the faces of the structure. So for this given face, let's consider the upper plate now. For the upper face, you have an atom centered or a central atom there. Now, this same upper face directly beneath, which is under, which is directly opposite the upper plate, we also have another central atom directly opposite the upper plate. These two atoms combine together to provide 1 full atom. So this is called a central atom. So let's find number of central atoms. So that is equal to, we've already obtained the first one, which is 1. So this face and this face combine to provide 1 full atom. Okay, now considering this face now, considering this other face, this face also provides 1 atom. Okay, we have a central atom at that face. Now, directly opposite this face, which is now the one behind, we also have another central atom directly opposite that face, and the two of them combine together to provide 1 full atom. So we also have here plus another 1. And finally, considering this outward face, which is simply this, this, and this, and this. So this outward face is also having a central atom. Directly opposite the outward face is the one inwards, which is this, also having a central atom. Now the two atoms combine together to provide 1 full atom. So we simply add plus 1. So that is the end. The whole of this is equal to 3. Therefore, number of atoms from that formula, the number of atoms become the sum of the corner atom and the center atom. So you simply add them together. That gives you 1 plus 3, which is equal to 4. So always keep this in mind. For a face center cubic structure, the number of atoms is always taken as 4. All right. Now, having obtained the number of atoms, we need to now find volume of atoms. The volume of every atom are spherical in shape. So their volume is simply the volume of a sphere. Therefore, volume of atom is equal to 4 all over 3 pi r cube, which indicates the volume of a sphere. Now, having obtained this, we are up next to what? Finding the volume of the cube itself. There is what is called a lattice constant or a lattice parameter. A lattice constant is simply the separation between two corner atoms. So I have a corner atom here, I have a corner atom here. The distance between these two corner atoms is called A, which is the lattice parameter. Similarly, I have a corner atom here, I have a corner atom here. Distance between these two corner atoms is also called A, which is the lattice parameter. So the separation between two corner atoms are called the lattice parameter. Now, we need to express the lattice parameter as a radius function. To do that, we need to identify what is called the closely packed region. The closely packed region is that region on the structure where the entire atom can touch themselves. In this case now, since I have central atom at each of the faces, you realize that if I draw a diagonal line from here through the center, these atoms can actually touch themselves. Let's take out a one-dimensional view to explain this. So I have my simple cubic structure, which is this. Not forgetting my corner atoms, not forgetting my corner atoms, not forgetting my corner atoms. These are my corner atoms, but for each of the faces, we have the central atom. So which means the entire atoms are touching themselves through the center. So if I draw a diagonal line from here to this place, this diagonal region is called the closely packed region, which in this case is the center. Since all the faces has a central atom, that simply means any of the face can be chosen as the closely packed region. So let's just pull out this particular face. Now let's observe something, that the central atom is offering its entire diameter. So which means we have here to be what? 2 times radius, because the central atom or the diameter is simply 2 times radius. Since the central atom is offering its entire diameter, we have that to be 2r. But the two corner atoms are not offering their entire diameter, rather they are offering just their radius apart, just their radius. So which means the total length of this diagonal, which is the closely packed region, let's draw a right angle triangle to indicate what we'll have on that board. Okay, so where the hypotenuse arm remains from this point to this point, let's label here as A, B, and C. So the hypotenuse arm is the longest arm, which is the diagonal region or the closed packed region. So if you sum them up, you have r, which is the radius of the first corner atom, plus 2r, which is the entire diameter of the second corner atom, plus r, which is the radius of the other corner atom. And if you add this up together, you have this to be what? 4r. So which means this hypotenuse arm is simply what? 4 times radius. But not forgetting, we have corner atoms, we have corner atoms, we have corner atoms. Now, distance or separation between two corner atoms from A to C, we call that the lattice parameter, in this case A. So A to C is simply A. Also from C to B is also A. And you have which are the lattice parameters or lattice constants. Now, we want to find the relationship between this lattice constant and the radius. So which means, since this is a triangle, we are going to be employing our Pythagoras theorem. The square of the hypotenuse arm is equal to the sum of the square of the two adjacent arms. So we have AB squared to be equal to, we have AC squared plus AC squared plus BC all squared. What then is AB? Remember, AB is 4r. So in place of AB squared, we have 4r all squared. This is going to be equal to AC squared, and AC is A. So you have A squared plus also BC is also A. So you also have A squared. So this implies, remember, now you have 4r squared. That means 4 squared gives us 16 r squared. This is equal to A squared plus A squared gives us 2A squared. We are targeting to make A the subject of the formula. So we divide both sides first by 2, which is the coefficient of A squared. We are going to have that A squared is equal to 16r squared all over 2. This simply implies that a squared is equal to 16 divided by 2 gives us 8. We put down an arrow squared. But the intention is to find a. So we have to take the square root of 8 r squared at this point to make a subject of the formula. Okay. So we can continue doing that over here. So a becomes the square root of 8r squared. But not forgetting that 8 can also be written simply as 4 times 2r squared. So a is equal to square root of 4 can be found, that's 2. Square root of r squared can be found, that's r. So it means 2 is left in the square root. So we have square root of 2. So keep this in mind always. For a face-centered cubic structure, the lattice constant is always equal to 2r times root 2. Now, we need to find volume of the cube from the formula, which means we have to find the volume of this simple cubic structure. Now, for a cube, the volume of every cube is simply the length of the cube to the power of 3. So, to find the volume of this cube is simply volume of cube equals a to the power of 3, because the length of each of these cubes is a lattice constant, which is a. Having found the value of a here, we can find the volume of that cube. So I'm going to have volume of cube to be equal to a to the power of 3, that is 2r root 2, all to the power of 3. So this is going to be equal to 2 to the power of 3, that's 8. R cube, you have r cube. Now let's find root 2 to the power of 3. So root 2 to the power of 3 gives us, okay, times 2.83. Now we find 8 multiplies 2.83. This implies that volume of the cube is equal to, let's find 8 multiplies 2.83. That gives us 22.64 r to the power of 3. So this is the volume of the cube. Now, if you know the volume of the cube, you know the number of atoms and the volume of atoms, you can find the atomic packing factor for the BCC structure. So let's do that over here. So the atomic packing factor is equal to, remember, number of atoms, and the number of atoms we obtain here as 4. So you have 4 multiplied by the volume of atom, which is the volume of a sphere, 4 all over 3 by r cube all over the volume of the cube, which we obtain as 22.64 r cube. So divide 22.64 r cube, not forgetting, multiply by 100%. So atomic packing factor is equal to, so you observe that r cube cancels r cube, so this 2 is off. Now you have 4 times 4, that gives you 16, multiplies, I have pi here, and pi is equivalent to 3.142 all over, remember there is 3 there, all over 3. Now let's put 22.64 up. It becomes 3 times 22.64 multiplied by 100%. So this is going to be equal to, let's obtain 16 multiplies 3.142. That gives us 50.272 all over, let's obtain 3 times 22.64. That gives us 67.92. Not forgetting, multiply by 100%. So this simply implies that for a face-centered cubic structure, atomic packing factor is equal to, now we find 50.272 divided 67.92. So we have this to be approximately 0.74 multiplies 100, and this 100%, and this simply gives us 74%. All right, so that's how to find the atomic packing factor for a face-centered cubic structure. I hope you find this video very interesting and helpful. Please, if you do, I would like you to encourage my work by liking my videos, commenting nicely, sharing to your friends, and if you're new to the channel, do well to subscribe as well. In the next video, we are going to be delving into the planar density and the planar packing fraction for each of these cubic structures. I hope to see you in that video. Thanks.